In this video, we are going to discuss about the non-ideal IV characteristics of MOS transistor. On completion of this topic, students will be able to explain the electrical properties of MOS transistor, and also they can explain the body effect and its effect in the MOS device. So in the non-ideal IV characteristics, first, this non-ideal transistor behavior has velocity saturation, mobility degradation, channel and modulation, body effect, subthreshold condition, junction leakage, tunneling, temperature dependence and geometry dependence. So this velocity saturation is nothing but this has at high lateral electric current, this carrier velocity rolls off and this carrier scatters off this atoms in the silicon lattice, and when this velocity reaches this VSAT, this electrons will be 10 power 7 centimeter per second and holes is 80 to 10 power 6 centimeter per second. So you can see this V value was mu E effective E divided by 1 plus E by EF, E less than EZ, and V saturation E is greater than EZ. And the next one is channel length modulation. So channel length modulation is here this reversed biased PN junctions form the depletion region, and this region is between the N and P with no carriers, and also this width of this depletion region grows with respect to this reverse bias. So we write this equation L effective is equal to L minus LD, that is when we have the shorter L effective, then it gives more current. So ID's value increases with respect to the drain source current, and also it decreases with respect to this voltage. So here you can see this source, gate and the drain, and the depletion width is shown here. When this charges when there is a reverse region occurs, this depletion region forms a width of L. And next one is channel length modulation, that is ID's values is equal to beta by 2 into VGS minus VT the whole square, where lambda we write it as channel length modulation, which has not future in size, and also empirically it can be fit to the IV characteristics. And the body effect, so far we have considered that the source and the body terminals are both connected to each other into the ground. So but what if the body is not connected to the source? Means if the body is not connected to the source and it is not connected to a different potential, then this causes the threshold voltage to vary according to this formula. So from the above formula we can infer that the threshold voltage increases with the source voltage and decreases with the body voltage. So subthreshold leakage, so this subthreshold leakage is nothing but this can be exponential with the VGS, and we write this equation as IDS is equal to IDS naught into E power VDS minus VT divided by NVT. So here you can see this P substrate and the N well substrate. So this junction leakage is nothing but this is because of the channel, that is current not passing through the capacitor ideally. So this decreases with the oxide thickness between the gate and the current. So this causes reverse biased PN junctions and has some leakage, which has the ordinary diode leakage and band to band tunneling and gate induced drain leakage. So here this reverse bias PN junction have some leakage at some negative voltage. This depends on the doping levels, and this perimeter of this diffusion layer also increases. And here we can see the ideal characteristics, which is in the cutoff region, linear region and saturation region. So if VGS is less than VT, then IDS value will be equal to 0, and if VDS is less than VD saturation, it operates in the linear region, as well as this IDS value is equal to beta into VGS minus VT minus VDS by 2 into VDS. And in case of the saturation region, VDS value is greater than VD sat, hence this IDS values is equal to beta by 2 into VGS minus VT the whole square. And you can see the simulated this NMOS and the PMOS plot. So the saturation region is given, a cutoff region and the active region is shown here. and if the current is on and off means if current is on it operates in the saturation region, and if it is off it operates in the cutoff region. And the electrical fields effects, so here it produces the vertical electric field. When a vertical electric field is produced, it is equal to VGS divided by TOX. So this attracts the carriers into the channel and forms a long channel. When this lateral electric field is given, it accelerates the carriers from drain to source and forms the long channel. Mobility degradation, so mobility degradation is nothing but here this high electric that is vertical electric field is effectively reducing the mobility. That is, the mobility term in this equation can be assumed to be independent of the vertical electric field. That is reasonable approximation when the electric field is weak, but if it breaks down for the stronger electric fields, and stronger vertical electric fields will be produced by the high gate voltage that can attract the charge carriers traveling along the inversion layer, and it can cause collide with the oxide interface. So this kind of effect causes mobility degradation, where this effective mobility decreases with respect to the gate source voltage. So that equation is given here. And this velocity saturation IV characteristic, so here under strong lateral electric field which is produced by the VDS, this charge carriers are accelerated, and the collisions between this charge carriers and the silicon lattices also increases. So beyond a certain level of this electric field, this carrier drift velocity saturates at a point we call it as VSAT, or we call it as velocity saturation. So to note this transistor saturation and this velocity saturation are two different things, so but they can be result in the saturation of the current through the channel with respect to the VDS. So we write this equation with respect to the length of the channel. The effective electric field for the same VDS increases with the increase in the strength of the lateral electric field. This charge carriers of the charge channel becomes velocity saturated as more higher VDS as compared to the long channel device. And in the case of threshold voltage effects, so here this long channel enters into the saturation, and in the case of this short channel device, this can enters into the velocity saturation region. So here this VTS is VGS, for which this channel starts to invert. So here this as voltage, threshold voltage is assumed to be constant, and it is really depending on the strong weak on which almost every else. So first one is body voltage, and second one is drain voltage, third one is channel length. And this when it is in the linear region, you can write the equation as this, and DIBL. So here this electric field from the drain affects the channel, and also this can be pronounced in most of the small transistors, and it causes this drain induced barrier lowering. So in this cases, this current will start increase at the high drain source voltage. Short channel effect. So in the short channel effect, in small transistors, source to drain depletion regions are extended into the channel, and it impacts the amount of the charge required to invert this channel. And the short channel effect, this VT increases with respect to the length. So some process can exhibit with the reverse short channel effect, in which this VT decreases with length. And the leakage, when what about the current in this cutoff region? The simulated region, this goes to cutoff region, or what differs and does not goes to the saturation region or cutoff region. And the case of leakage sources, it occurs in the subthreshold condition. This transistors can't be abruptly turned on or off, and also dominant source in the contemporary transistors. In the gate source gate leakage, this tunneling through the ultra thin gate dielectric, junction leakage, reverse bias to PN junction diode current. And the case of the subthreshold leakage, this can be exponential with the VGS, and also we can rewrite this equation according to the linear saturation as well as cutoff region. So the gate leakage carries tunnel through very thin gate oxides, and also it is very constants greater for this electrons and negligible for the older process, and also it is important for the 65 nanometer. To band tunneling, this tunneling occurs heavily doped PN junction, especially the side walls between the drain and the channel. Also increases the junction leakage to the significant levels. So that equation is given here. And gate induced drain voltage, this occurs at the overlap between the gate and the drain. Here we can reduce the subthreshold by applying the B substrate values to the drain leakage. Temperature sensitivity, here this increases temperature with a reduced mobility, reduced threshold voltage. When current is on, it decreases with temperature, current is off, it increases with temperature. So the graph is given here. So what if the transistors are not ideal means it acts like a switches, but these transistors, these effects matter for supply voltage choices, logical effect, power consumption, pass transistors, and temperature of operations. Quiz questions on non-ideal IV characteristics. Derive the noise margins of the CMOS inverter. Thank you.